다음은 하시코프 공동창업자 겸 CTO이신 아몬 데드가께서 키노트를 진행해 주시겠습니다. 본 세션은 동시 통역이 진행됩니다. 테이블 위에 통역 수신기를 착용해 주시기 바랍니다. 아몬 데드가를 큰 박수로 맞이해 주시기 바랍니다.
Thank you. Thank you. Thank you. Well, thank you all for making the time to come and be here today and spend some time with us. If you haven't seen it yet, there's the little translator. So unfortunately, I don't speak great Korean, but hopefully we have a wonderful translator. So I hope everyone will be able to follow along. This is actually my first time in Korea, and I'm so impressed with this event that if everyone's okay with it, I wanted to take a quick selfie from the stage and get everybody with it. And I'm going to post this on my LinkedIn later. Awesome. Thank you. I'll take a picture of everybody here, too. As it sounds like I don't follow perfectly, but I could understand PowerPoint and whiteboard, so I think I was being made fun of for my lack of PowerPoint here. But many of you have probably seen some of my videos on YouTube, and you might know that my favorite medium by far is whiteboard. So I thought today I would use this and use the strategy day today to really talk about, what does HashiCorp do, what are our tools, and ultimately how we think about the zero trust strategy. And I thought let's keep it interactive and do it all as a whiteboard session. So, for those of you who don't know HashiCorp, I'll start at the top and we'll kind of give you a light introduction to the whole portfolio. But then we're going to go a little bit deeper and spend more of the time on the security tools and some of the security portfolio. So more specifically on Vault, Consul, Boundary, and some of those tools. And then later today, you're going to hear from other guest speakers. We have a great speaker talking to us about Nomad. So you'll hear from Justin later today. And then after that, you'll hear about a Terraform as well. So with that, I'm going to start at the high level. If I describe what HashiCorp solves, the first problem we really think about is how do we help developers in their mission to deliver applications? If I think about, for almost every organization, that's the real business value. That's what we care about, right? The applications are where we're delivering new features for our customers or solving new problems for the business. Everything underneath that is really a detail, right? For better or worse, we have to spend a lot of our time on those details. So that's where our operations and platform teams and security teams are focused, is how do we deliver underneath that the infrastructure that the applications run on top of. And I think what's making that infrastructure much more complicated these days is that this is highly fragmented, right? It used to be that everything was in our private data center. Now it's private data center plus AWS, plus Azure, plus GCP, plus many other solutions, right? Those might be, regional clouds, or if you're operating in China, maybe you have to use Ali Cloud or other different solutions like Oracle Cloud. So there's many, many different infrastructure platforms that we now need to support. And so when we think about what's the role of HashiCorp, what's the problem we really solve, we sit in this middle box. And the problem we aim to solve, I don't know why this keeps disappearing. So the problem we try and solve as HashiCorp is two different problems. One is on this right-hand side where the applications and the infrastructure are, is how can we have a single pipeline to deliver our applications in a way that's going to be consistent across all those different environments. So you can think about it for these application teams as what we want is a consistent approach to building our applications. Meaning I want to have one process to deliver my app, whether that app goes on Amazon, whether it goes on Azure, whether it goes on Google. I don't want to have 3, 4, 5 different ways of building my application and maintaining it. On the other side is what's the relationship between our developers and the platform teams. So if I think about traditionally how these two teams work together, everything is intermediated by a ticket. If my developer wants more compute, I file a ticket and I wait a few weeks. If I want to update a firewall, I file a ticket and I wait a few weeks. If I want to update a network, I file a ticket and I wait a few weeks. And so that's been the experience of developers for a very long time. And I think the challenge then is for our development teams, everything goes very slow. Anytime I want to make a new service or make a change, that might take weeks or months to deliver. So I want to move away from a ticket-driven experience and really make it more of an API-driven interaction. So as an operations team or as a platform team, I want to deliver a service, I want to deliver a platform that is API-driven, and now my developer can consume that either in their CI/CD pipeline, they can consume it through a UI interface, or they can consume it directly as an API and do it in an automated way. So now if my development team wants to deploy 5 times, 10 times a day, they can do that. They don't need a file ticket and wait, right? So the goal is really for these teams is how do I enable them to have self-service? So if I zoom out and really think about what HashiCorp tries to solve, it's these two things. How do I enable my developers to have self-service, but in a way that is secure, in a way that's compliant, in a way that we don't lose control? And at the same time, how do we do it in a way that's consistent in a multi-cloud world? So I want to have one set of tools, one set of process that will work across my private data center, my public cloud, and all my other environments, right? So to make that happen is obviously a complex challenge, right? It's not one tool, it's not one problem. So if I talk about HashiCorp then, there's many different tools in our portfolio that solve different problems. So you can think about the company as having 4 layers of focus. One is provisioning, and here our biggest product is Terraform. And then underneath Terraform that helps it is Packer. And you can think about the philosophy of both of these tools as very similar. They're both about infrastructure as code. So with Terraform, I want to describe in a template, in a blueprint, using an infrastructure as code approach, what are all of the components of my infrastructure? So those components might be something simple, like let's say I have 3 VMs. Those VMs sit behind a load balancer. And then in front of my load balancer, I have a DNS record, right? So this might be and then the VMs talk to a database. This might be a very simple 3-layer application, right? Web app with a database, with a load balancer, and a DNS record in front of it. So I can describe all of that as code with Terraform. That lets me then hand that into Terraform. And Terraform is going to figure out, what do I need to do to make your infrastructure real, to make this picture come to life? And so that might require talking to many different providers. We might say the VMs are provided by VMware. The load balancer is an F5 device. DNS is provided by Dyn. Maybe I have to provision a MySQL database. So Terraform supports talking to many, many different things, but it's going to talk to all of those things and talk to their native APIs to create the infrastructure you want. And so what that allows us to do is then evolve our infrastructure and manage it all as code, as software. We check in the configuration to GitHub. We manage it just like we would manage our applications. And now we can build pipelines around how we manage infrastructure safely. You can think about Packer as very similar to this. So with Packer, again, it's an infrastructure as code description. I might say I have a Red Hat image. On top of Red Hat, I need to run some configuration management. And then on top of my config management, maybe I have additional security controls. And I'm going to feed that into Packer. And then Packer will build me different machine images. So it can build me an AMI image on Amazon. It could build me a VMware image on-prem. It could build me a container image. So Packer becomes one tool to have this pipeline of describing the image as code and then building it in an automated way. So you can already start to see, how do these two solutions, Terraform and Packer, fit into this picture? Well, what they allow us to do is build that consistent pipeline, right? With Terraform, I can have that one workflow, that one pipeline, and it doesn't matter if that infrastructure is on Amazon, Azure, or Google. Same with Packer. I have the one pipeline. I can build the images for all of those things. What that allows is that I can run Terraform or Packer in my CI/CD pipeline, and now my developers get that self-service experience. So you can start to see how these products fit into this bigger goal. Now, at the next level up is security. And here we have 2 key products. One is Vault, which I'll talk about in a lot more detail in a moment. And the second is Boundary. And at a high level, you can think about the difference between them as Vault is designed for machines talking to other machines, so machine to machine. So if I have a web server that needs access to a database credential, like in this example, these VMs need a database credential to be able to talk to that database. They need a username and password. They need a certificate. How do they get those in a secure way? That's what Vault tries to solve. Then Boundary solves the human side of this. So when I have humans trying to access a machine, so I might be a developer and I need to get access to the database to debug something. How do I securely get access to that database? That's this problem Boundary solves. So we'll come back and talk about both those in more detail. Then the next layer up is thinking about connectivity and networking. This is where our Consul product fits. And it really solves the machine-to-machine challenge, right? If I have these different applications talking to one another, I have a problem of how do they discover one another, right? My web server needs to know the IP address of the database. I also need the ability to segment and prevent that access. So how do I say the web server is or is not allowed to talk to that database? So it's about segmentation of the network. It's about discovery of these different services. And then when you talk multi-data center, it's supporting applications that are global. So I might be in Amazon, and I need to talk to an app in AWS, or I'm sorry, in Azure. Or I'm in Azure, I need to talk to a database in my private data center. So how do I support that global networking? Then at the top level here is the runtime. And here's our Nomad product, which, if you're not aware of it, you can think about it as somewhat similar to Kubernetes. It's an application scheduler that lets you deploy and manage every type of application. It could be a container. We support VMs. We support WebAssembly functions. It can be Java binaries or static binaries. So it's a very powerful, flexible scheduler that supports all sorts of different workloads, not just containers. And then Waypoint is our newer product at this layer, which is a developer portal that looks at how do we abstract and hide all the details of this infrastructure so our developers don't have to know about all these different layers. They can just focus on what they want to do, which is build their application, deploy their application, and not have to think about how the infrastructure works. So if you think about HashiCorp in the context of your other tools, to the left of us is pre-production. So here's where you can think about your version control system, right? So GitHub, for example, your CI tool like Jenkins. You might have an artifact management tool like Artifactory, or static code analysis if you're using something like Sneak. And then to the right of HashiCorp, across all of this, is observability. And that might be Splunk or Datadog or New Relic. You can kind of think about the different providers there. So HashiCorp doesn't solve the ones to the left. So everything in pre-production, we integrate with GitHub and GitLab and Jenkins and everybody there. And then to the right, we also integrate with Datadog, Splunk, Sumo Logic, everybody in observability. Now, above all of this, up here, is where the applications run. So your applications sit at this top layer, the applications and their middleware, so databases and things like that. And so this bigger picture that I draw with all of these pieces is what we at HashiCorp will call, and you'll see us talk about, a cloud operating model. And so when we talk about a cloud operating model, what we're talking about is this architecture, this set of different software and applications that collectively allow you to solve for this picture, right? Because our view is every major company, every large organization will be a multi-cloud business, right? You'll at least have a private data center in one cloud, if not multiple clouds. So the challenge is, as an architecture, how do you design for that? And our view is this ends up being the kind of picture we've seen over and over again from working with thousands of enterprise customers around the world, is that these are the common pieces. And you can see that in some sense, any one of these pieces, if I try and remove them, if I say I don't solve for that, then you just create a problem for the application that sits at the top. Because fundamentally, a production-grade application needs all these pieces, right? Yeah, you could argue maybe I don't need observability, but then is it a production-grade app if you don't have logging, if you don't have telemetry, if you don't have visibility? No, you need that if you're a production-grade app, right? Same thing if you talk about something like Vault. You could remove Vault and say, I'm just going to hard code usernames and passwords in my app, right? Okay, it will solve the problem, but it'll create 3 new ones. And so I think if you're really saying a production mature application, you end up needing all of these pieces. So our view is, as a platform team, right, as organizations mature, the goal should really be, how do I deliver all of these as a service to my application team and my developers so that they don't have to think about it? So that every app I build, I have a standard way of doing provisioning, a standard way of doing source control, a standard way of doing, secrets management, so on. So this is sort of the bigger picture. Now, from here, I want to focus in, and we're really going to talk more about the security layers and the security impacts of this, and talk about zero trust. So when we talk about zero trust, I think it helps to understand, I'll call it the current state, right, or how we generally think about network security in most organizations. So the analogy I like to use is, I think most people's approach to network security is what I call castle and moat. You have the four walls of the data center that you protect, and then you bring all of your traffic over the front door. And over that front door, we put a lot of different protections, right? So we try and say 100% of my threats, I stop at that front door because I'm using a firewall, and I'm using a WAF, and I'm using a SIM, and advanced threat protection, and all sorts of fancy approaches. And so my model of how I think about the world is that my attacker is on the outside of my network, and the outside is bad, and it's dangerous. And the inside of my network is good. It's high trust, it's secure, it's confidential, and it's inside the four walls of the data center. Right? This has been the classic approach to network security for 30 years. And so now you take this model and you try and bring this to the cloud. And so now you have these nice, fluffy clouds, and you connect all of them together into a giant super network. And now what you try and do is you try and extend that model of the data center and say, I want my cloud to be 100% secure as well. And I'm going to bring all my traffic over the front door. And what you start to realize is that these two are very different worlds. Right? In my private data center, I have a cable that comes through the wall, and it goes into my firewall. And so if I want to bypass that, I have to call someone in the data center and say, can you move a cable around the firewall? If I'm in Amazon, I make one API call, and I say, make my S3 bucket public. And Amazon says, 200 OK, it's on the public internet. Right? So 10 milliseconds later, that thing that I thought was private is now sitting on the public internet. And so you start to realize that the perimeter in the old data center was a real thing, right? There was walls and cables, and it was a physical construct. In the cloud, it's an idea. The perimeter is a virtual concept. It's an idea. And so your level of control is much, much lower. And if I'm going to give people the capability to do anything in cloud, I give them keys, it's very easy for them to make a mistake, right? To open up a firewall rule that they shouldn't, to mark something public that they shouldn't. And so you either give people no ability to do anything, or if you let them do it, you accept that they might make a mistake, right? And so then this 100% becomes very impractical. And so, my view is treat it as 80%. Some people will argue with me on that number. They will say, we're very good at security. Our engineers know what they're doing. It's not 80%. It's actually 99.9%. Okay? Other people will say, on a good day, my engineers don't know what they're doing. So, maybe it's 50%. I think you can pick any number you want as long as it's not 100%. Because the moment you pick anything that's not 100%, the assumption, the operating model changes. Now your attacker is assumed to be on network, right? And that's a totally different assumption. In the old model, your attacker was on the outside of your network, and I trusted it. Now in this new model, my attacker is on my network, right? Whether I said it's 50% secure or it's 99.9% secure, I think about the 0.01, and in that 0.01, my attacker is on my network. So this all of a sudden becomes a totally different approach to how we think about network security, right? Because in the old world, we did all sorts of bad things, right? If I had a web application that wanted to talk to a database, where did it get the username and password? Well, I just hard-coded it. It was in the application source code, or it was in the application's configuration file. And we said in this old world, that's okay, because the web application is behind the four walls, the database is behind the four walls, and our source code is behind the four walls. So everything is good and safe. Now in this new world, well, our attacker is also behind the four walls. So anyone who's on the network who has access to GitHub now knows the database credential and can connect to it, right? And so I think there's a lot of different, reactions in some sense to this. One reaction we often get is, how do we go back to the old world? How do we go back to 100% secure, right? That was a good world. Let's just go back, right? And my view is that world was always a lie. It was always, in some sense, make-believe. Because what we assumed to get to 100% is that you never made a mistake in your firewall. You never made a mistake in your WAF. You never had an unpatched application. There was never a zero-day vulnerability. You never had an employee who worked for you who was malicious, right? And so the reality is all of those things are true, right? You can't be a large organization and assume you never make a mistake, or that no one who works for you is malicious, or that there'll never be a vulnerability, because we know that's the reality. And so when you look at all these very, very large breaches, right, whether it's Google, whether it's Capital One Bank, whether it's any of these very large, high-profile security losses, you see over and over again that this does fail. People do get network access, right? And so I think this really becomes the heart of that shift to zero trust security. Right? So what does zero trust mean? Right? I think it's become a very popular term. Lots of vendors are using it. So I think it's helpful to explain, when I say zero trust, what do I mean exactly? And for me, I mean two things. One is that it's an explicit, authentication and an authorization that's required for every action, right? So I don't care whether you're a user or an application or a machine that's making a request. I need to authenticate what's the client. Are they a user? Okay, it's Armon. He's a developer. He works for HashiCorp. Or it's a web application called A talking to a database called B. Okay, I need a strong notion of the identity of those applications. And then I want the authorization, the rule that says A is allowed to talk to B, or Armon is allowed to talk to the database. And if that rule doesn't exist that says I'm allowed to do it, then the default policy is that it's denied. So it's a shift to a default deny policy. And I think both of these things are very different from the model of the old world. In this old world, there was no explicit authentication or authorization. If I was in the private data center and I was on the right network, I could just connect to the database, right? If there was a firewall that was, sitting in front of the database, it might prevent me from connecting. But the default is allow. So that's the difference, is you go from a world where the default is allow to a zero trust world where the default is a deny. And the reason that's super important is if you think about a large enterprise network, there might be 10,000 things, 50,000 things that you want to allow, but there's millions and millions of things that you want to deny. So trying to manage that list of the millions and millions of things that you want to deny is just not practical. You're going to make a mistake. You're never going to capture every one of those edges. It's much easier to actually manage the smaller set, which is the things you want to allow, right? So those are the two things that, to me, are very critical when we talk about this shift to zero trust. Next is, how do you actually enforce a zero trust or define a zero trust posture? If we think about, again, the old world, everything here was an IP-based control. Meaning I had firewalls and I had VLANs and I had security groups, but they all were based on an IP. I said this IP can talk to that IP. This subnet can talk to that subnet, right? This CIDR can talk to that CIDR. And so if you said, okay, that made sense in the old data center, things were pretty static. You had VMs with long-lived IPs. But now in a cloud world, you start to say, okay, well, I have a container, and that container, its IP changes, who knows, every few minutes, right? I'm deploying it on Nomad or on Kubernetes. It's auto-scaling up and down. the IP changes all the time. And so now if that container is trying to talk back, if it's trying to talk back to a database, let's say, can I define a firewall rule with a static IP when the IP changes every 5 minutes? Not really. It becomes very impractical. It's very hard to define that rule because it's changing so often. And then if you start to say, okay, well, now I'm going to embrace serverless and use things like Lambda, now it's even worse. Now your Lambda function only lives for 1 second at a time. Are you really going to update the IP address of the firewall every second for the Lambda? Right? Like, it becomes very impractical. So as we think about moving to a cloud world, that kind of IP-based approach to security becomes very complex, right? Because the IP's changed, the machines are very dynamic, your Lambda functions come and go. So the heart of, I think, then implementing Zero Trust correctly is really a shift to an identity-based control model. So I don't want to define my rules based on IP. I want to define them based on identity. Meaning I want the rule to say something like application A can talk to application B, not IP1 can talk to IP2, right? The challenge of an identity-based model is that identity doesn't exist in the network, right? You have source IP and you have destination IP, but you don't know the identity. So when we think about how do you implement a zero trust strategy then, to me there's 4 key pillars to this, right? The outer 2 pillars are about establishing identity. So you have human identity on one side, you have machine or application identity on the other side. And so human identity is the one we understand best, right? This is single sign-on with a common identity provider, right? And so this might be something like, Azure AD or Okta or LDAP. There's a lot of different techniques for the human identity. This is probably the most well understood. We've been doing this for a long time. On the other side, with machine identity, that's the heart of the problem that Vault actually solves. So when we talk about Vault as a solution, the key thing, the first thing that it's really trying to solve is what we call identity brokering. And what do I mean by that? I mean that applications, when we run them, they have an identity, but it's very fragmented, right? It exists everywhere. So if you think about an application, well, I have an application running on Amazon. That application has an IAM identity. If it's running on GCP, it has a different IAM identity. If it's running in my private data center, maybe it has an Active Directory service account. If it's running on Kubernetes, it has a Kubernetes service account. So each of these are different forms of identity, right? They all mean different things, but the Kubernetes identity doesn't mean anything to my Active Directory identity. My Active Directory identity doesn't mean anything to GCP. So these identities don't translate between these different platforms. So the goal of Vault is to act as a central broker to let me define policies and move between these different boundaries, right? So I might have an application, for example, running on Kubernetes. It's able to connect to Vault and prove its identity. And now I can write a policy for, let's say, that application foo. And that policy is based on the identity of that application, not the IP address. I don't care, is there 1 copy, 10 copies, 1,000 copies of that application running. It has the same identity, and so I want the same policy to apply to it. And so this lets me start doing and solving different problems, right? The first problem people often think about with Vault is they think about it as a secret manager. And this is the most sort of obvious use case, because effectively we write a policy that says you're allowed to read, a set of keys, so we have a key value store, and I write a set of keys for foo. And so that could be, a username password, it could be an API key, it could be a certificate, it could be whatever you want. It's effectively a key value store. And so as a key value store, the keys are encrypted, they're stored centrally within Vault. The application has to authenticate and be authorized to read out of that key value store. So all of a sudden you say, okay, well, Vault is a secret manager. It solves this problem of reading and writing secrets. And so that's how people think about Vault. But it's actually a very limited way of thinking about it. What really starts to become interesting with Vault is not just static secrets. Because with a static secret, you still have this question of, well, how did this username and password get put into the Vault? And how often am I changing that username and password? And is that username and password being shared between 100 different systems? So instead, you start to think about moving beyond static secrets with Vault to what we call dynamic secrets. So the idea is I don't want to put that username and password in a static way within Vault at all. Instead, I want to say the application has read-write access to my database, let's say Oracle. And I'm not putting the actual username and password in Vault. I'm just putting a policy that says it has read-write access to Oracle. And now when that application, in this case, the foo application, talks to Vault, and it says, give me my database credential, Vault will actually connect to the database and create a new dynamic credential. So we're going to create a new user. So create user X, and create it with a dynamic password Y. And we're going to restrict what that user is able to do, so we'll grant only the Z permission. So we'll scope down what the application can do. And then we're going to give that username and password to the app. So we'll say, here's X and Y. Here's your username and password you can use. And by the way, it's only useful for 7 days. At the end of 7 days, Vault will connect back to the database and say, delete user X. So drop X, right? So if you think about what this changes now, fundamentally, we don't have to create the username and password in advance. We don't have to think about rotation of that username and password, every 30 days, 90 days, 360 days. And we don't have to think about cleaning up credentials when they're not used anymore. That entire life cycle of creating the credential, restricting what it's useful for, rotating it, and then deleting it when it's no longer needed is now automated by Vault. And so from an application perspective, the application is able to use X and Y for the first 7 days. And then somewhere in between, it's going to talk to Vault and get a new credential. So it's going to use A and B. And then somewhere in between that, it'll switch to a new credential, C and D. And Vault's going to come behind and clean that up. So now we don't have these long-lived credentials that are sitting in our environment. And I think this is one of the biggest risks we see is even if you move all of your secrets into a system like Vault, even if you move all of them into a secret manager, if you're not rotating them all the time, a secret doesn't stay a secret. And a great example of that is if you look at the Capital One bank breach, right? They had an Amazon cloud key. They gave it to an application. The application logged that credential to Splunk. Someone did a backup of Splunk, and that backup was accidentally exposed. So the attacker got to the backup of Splunk, searched through that for passwords, found the cloud credential, the Amazon key, that was still valid 5 years later, and they started using that key to steal data out of their cloud account. And so what made that attack possible is that that key was still valid 5 years later, right? And I think it's not practical for us to expect that the developers will be perfect, that they're never going to leak a key. Because we know in practice, they're going to check it into GitHub, they're going to paste it into Slack, they're going to log it to Splunk, they're going to send it to Datadog. So the credentials will end up all over. So the only way to really be aggressive about that is you move away from static credentials to make everything dynamic. And so this example I used here with Vault and the database, Vault supports that with all sorts of systems. So we can do it with databases. You can do it with NoSQL systems like Mongo. You can do that with message queues like Kafka or Rabbit. You can do that with certificates. So if you think about PKI, we see this very often where people have very long-lived certificates, certificates that live for 5 years, 10 years at a time. And then developers take that 10-year certificate and they just put it in GitHub. And so if that certificate is ever leaked or it's ever exposed, there's no rotation story for that thing, right? It's just valid for the next 10 years. And so you can see with an approach like this, the application foo can come talk to Vault and say, I need a TLS key. and we can actually give it a very short-lived certificate that maybe is only valid for 48 hours at a time. And so that's the model a lot of our customers have moved to, is you don't have certificates that live for years at a time. They might live for hours, days. In fact, we have one customer that they don't live for more than 1 hour, right? So they've gone all the way down to 60 minutes, and you constantly rotate. In addition, you can think about this list being, on and on, right? SSH keys, cloud credentials, pretty much everything that has an API that allows Vault to create a credential, rotate the credential, and delete the credential. We can move into a dynamic world of management, right? So I think it's a very powerful concept, but it changes the way to think about Vault, which is it's not just a secret store for key value. Yes, that's a very basic use case. It's designed to allow us to move beyond storing the secrets into automating the whole life cycle of creation and rotation and deletion of the credentials, right? So what does that give you is, okay, now on this side, I have a strong identity of these applications, and I can write policy based on their identity. So if I come back to this framework, on one side now what I have is the machine identity, or the application identity. And on this side, I now have the human identity. So I know that's application foo, and this is human user Armon. So that enables you to solve then the middle two use cases, which is machine to machine. And then on the other side, it's human to machine. And so why are these different? If you think about machine to machine, I might have hundreds of applications or thousands of applications running on tens of thousands or hundreds of thousands of machines. And so at that scale, the network connections between all of those applications might be in the millions, right? You might have millions of different network connections. So you don't want all of that traffic going through central points of enforcement. I can't put a firewall in the middle of all of that and have millions of flows going through it. I'm going to create a performance problem, an availability problem, a latency problem. So architecturally, I want the machine-to-machine use case to be very distributed, very high performance to solve for that large-scale network. If I think about human-to-machine, it's the exact opposite. I don't have 10,000 people logging into a production environment at the same time, right? At any given time, maybe you have a few hundred or maybe a few thousand connections into production, but you don't have millions, right? And because it's a human user logging into a production environment, if I'm Armon and I'm connecting to a database, I want to know, did I steal any customer data? Like, what queries am I running? If I SSH'd into production, what commands did I execute? Did I install something I shouldn't have? And so I want to be in between the user and the system to understand what did they do. I want to record and manage that session to make sure the human user didn't do anything bad. So that's why architecturally they look very different. So this is where our Consul product fits, and this is where our Boundary product fits, because they each solve a different problem. So if we talk about Consul briefly, right, the core problem that we set out to solve is a very simple one. It's discovery. So I have application A, and it wants to talk to application B. How does A find B? Well, most of the time, A hard codes an IP address. It always wants to use, IP1 to talk to B. Now, okay, very quickly you run into the problem of what happens if B crashes and I've hard-coded the IP. So you say, okay, I'm going to solve that by basically just hard-coding the IP of a load balancer. So I'm going to go to a load balancer. Load balancer will go to B, and now I can have multiple copies of B. So now I have another problem, which is, okay, I've still hard-coded the IP address of the load balancer, but two, now I have load balancers everywhere in my network. And if I think about moving to a microservice architecture where I might have hundreds or thousands of microservices, I don't want to hard-code hundreds or thousands of IPs of load balancers everywhere in my infrastructure. Because the load balancers add cost, they add latency, they impact the performance of the application. So this is where the first problem Consul solves is really a discovery one. Is what I don't want to do is hard code an IP at all. Instead, what I want to do is use the name of the service So I can query console and say, I want to talk to service b.service.console. And this is a DNS lookup. And so when we see that it's the console domain, we're looking for a service. The service is called service B. Console will say, go talk to IP1. And if we have multiple copies of the application, we can load balance between IP1 and IP2. If IP1 fails, we'll route around and go to IP2. So this starts to change the architecture of how you think about discovery. Instead of hard-coding an IP, what I hard-code is a name. And that name can now point to a dynamic set of IPs. So imagine application B, for example, is running inside Nomad, or it's running inside Kubernetes, and now it's auto-scaling. So we might say at night, I only need 1 copy of B, but in the day, I go from 1 copy to 10 copies, and I'm going to scale up and down. So Consul starts to enable this very dynamic discovery of these different applications. At the same time, A and B might not be in the same data center. A might be in Amazon, B might be on-prem, or B might be in Google. So you can start to mix and match applications in different environments, different networks, and have them all connect to each other. Now the next challenge is, okay, but what about application C? It's not supposed to connect to B. What prevents C from just reaching out and connecting to B? Right? How do I prevent that access? And so in kind of the old world, we would have said, okay, well, I'm going to put a firewall in front of B, and everything that tries to connect to B has to go through this firewall, and I'm going to write a set of rules that say which IP can talk to which IP. So now, in the same way I don't want to put load balancers everywhere in my network and manage 1,000 load balancers, I don't want to put firewalls everywhere in my network and manage 1,000 firewalls, right? And so how do I think about this differently? So this really brings into sort of more of a modern service mesh approach. So what I want to define is a rule that says A is allowed to talk to B. Again, this is an identity-based rule, not an IP-based rule. And then what Consul will do is distribute a set of certificates. So we have a set of certificates for each of these apps that get provided by Consul that embeds the identity of the application. So the certificate for B encodes its identity as application B. For A, it encodes its identity as A. And now when they talk to each other, we go through a set of proxies. So this could be using Envoy, for example. And this forces us to use mutual TLS. So when A talks to B, it provides its certificate with its identity saying, I'm A. B provides its identity and its certificate saying, I'm B. And now we can explicitly understand the identity and authenticate both sides of this connection. Then when B gets that incoming connection, it can check and say, is there a rule? A is allowed to talk to B. If yes, then okay, we let the traffic through. So now if application C tries to connect to B, then it probably either doesn't have the certificate, or if it does have the certificate, there is no rule that says C is allowed to talk to B. And because this rule isn't here, we're going to reject this connection and say, sorry, you're not allowed to connect. And now I didn't need to put a firewall or anything in the middle of my network. In fact, the middle of my network could be anything. I don't have to trust the network at all because I'm encrypting everything with TLS. I'm authenticating all the connections. I'm authorizing everything. And so this simplifies my network design because I don't have to trust it and treat it like this very secure environment. In fact, this could be over the public internet. So some very advanced users like PagerDuty, they don't even have a private network. All of their VMs run on the public internet because they don't trust the network at all. They treat the network as just, it's the internet, right? So that's great for our modern new style applications. What about the legacy apps, right? Most legacy apps don't look like that at all. It's a Java app, going through a firewall, talking to, our Oracle database, and there's a rule that says IP1 to IP2, right? That's what most networks look like. They're not going to be modern containerized applications running in the cloud. So the challenge is how do we apply some of those same practices to a legacy environment. And this is where we integrate Consul with Terraform. So you can define a Terraform policy, so using infrastructure as code, to manage our firewall. And so this could be, we're using a Palo Alto firewall, or F5, or Fortinet, or Checkpoint, or doesn't matter, anything Terraform understands. But now the input to that Terraform script is not the IPs. We want to say, what's the different applications? It's the Java app talking to the database. The IP information we're going to fill in dynamically from Consul. So Consul will integrate with Terraform to provide that configuration data. So now imagine we deploy a new Java application. In the old world, I'd have to file a ticket against my firewall team and say, there's a new IP, please update the firewall. And then I wait 3 weeks, 4 weeks for someone to do it. Versus I can integrate with Consul, so the moment this application comes up, it registers with Consul. So we get a new app register with Consul. Consul detects there's a change in the set of Java services, and so we rerun and provide the new IP address of that Java application. And then when Terraform executes, it now updates the firewall and adds the new IP. So that's IP3 can also talk to IP2. That entire flow of registering with Consul, triggering Terraform, and updating the firewall can be executed in a few seconds. So one of our very large customers, UBS Bank, talked about in their private data center environment, they have 700 unique services spanning 4 different data centers with thousands of hardware load balancers and firewalls in their environment. It took them, on average, from the time the ticket was filed to the update was made to their network, 6 weeks for an application to get traffic. By adopting Consul and automating that flow of their network, they update all of their load balancers, their firewalls, and their API gateways in about 5 seconds. And they eliminated 3,000 tickets a month of adding and removing IPs, right? So when you start to think about what we can do with Consul, yes, the first problem is a simple discovery one. But what that starts to then enable is we can go from discovery into doing mesh or segmenting the network. And then based on that same data, we can actually do network automation by integrating with Terraform. And so you can start to see all of this the goal is the same thing, which is to get to this zero trust goal of defining an identity-based rule that says A can talk to B, and then hiding the IPs. I don't care what the IPs are, they're dynamic. So that's Consul over here, right? So you can think about those are the key use cases. So discover, segment with mesh, and then use that to do network-based automation by integrating with Terraform. So then the last one here is, what about human to machine? How does that work? So if we talk about human to machine, typically I have a human user, maybe they're working at home, so the first thing they need to do is connect to a VPN. Then I have a firewall that says, where can you go from my VPN? Then I go to a privilege access management tool to get the username and password, and then you take that and connect to the database. So this is very much the classic workflow, right? So what's the problem here? Well, one, I have to manage a set of username, passwords, or certificates for my VPN. 2, I've now given direct network access. So now users are on the network. That means I now have to manage a separate set of IP controls. And then over here, I have to manage another set of users and groups and another set of credentials before I can get to that system. So there's a lot of things I have to manage in here. There's a lot of complexity, especially if you think about a cloud world where IPs are dynamic, the actual hosts and users and groups are dynamic over here, and I have users coming and leaving my organization all the time. I don't want to manage all of that. So we looked at all this complexity and said, is there a way to kind of simplify this, to kind of collapse all 3 of those into one? And that's really what Boundary is. So if you think about boundary, oops, it runs at the edge of the network. And so the user connects directly to boundary, but they don't have a separate username and password. They just do a single sign-on with their identity provider. So I do a single sign-on with my username and password. I don't need a separate certificate or user credential to connect to my VPN. Now, this is very important, as unlike a VPN, boundary does not give the user network access. So I'm not going to put the user on the network. Instead, I'll define a set of rules that say, okay, my developers, they need access to the database. And so when the developer logs in, they'll see a list of everything they're allowed to connect to, which in this case might be only the database. And so they don't have access to the network to connect to whatever they want, anything on the network. They can only select one thing. And so when they say, I want to connect to the database, Boundary will initiate that connection for them directly back to that instance. So in that sense, it'll act as a reverse proxy. It won't give them network access. So if you think about that, that means now I don't need the second layer of firewall that I had over here. Because if I have multiple rules, let's say my business user has access to the BI. I have a BI system too. The firewall can't tell the difference. So the firewall is going to give you access to both the database and the BI tool because it can't tell, is the user a developer, is the user a business user? It has to give access to both. Boundary knows the identity of the user. So if you're coming in and you're a developer, you only get access to the database. If you come in and you're the business user, you only get access to the BI system. So in that sense, the firewall is actually much more looser. It's much more open than Boundary is. And then from a PAM perspective, I don't want to have another layer of tool. So Boundary will integrate with system like Vault and use its ability to do dynamic credentials just in time. So when the user wants a session to the database, they'll connect to Boundary, initiate that session, and then we can ask Vault to create a username and password for the database specific to that session that automatically expires when the user disconnects. So the moment the user disconnects, we'll delete that credential, right? And then I don't want to manage the set of IPs for things like the database and the BI system manually. So we'll integrate Boundary with tools like Consul or Kubernetes or the clouds directly. So you don't have to hard code the IP address of the database or the BI system. We'll query Consul dynamically, and it will have a catalog, or we'll query Kubernetes and ask its catalog, what's the IP address of that service? And so if the service is scaling up and down, or if it's moving around, that's okay. We don't have to keep updating the static IPs. So you can start to see how it simplifies this whole thing. We move away from static IP. We move away from static username password. We move away from static host management into a much more dynamic cloud world. So it fits very much into the same worldview where we really want everything to be very dynamic. So this is a much more sort of, if my pen will work here, or maybe not. What the heck? Okay, there we go. So it's much more of a dynamic approach, right? So it looks at basically a dynamic approach to identity, as well as basically looking at a logical authorization approach. Oh, okay, I don't know. This iPad pencil has decided to die on me. And so it's all based on identity as the core basis of the rules. So I know I'm a few minutes over here, but I'll kind of zoom out and summarize. So when we think about kind of the broader goal for us, again, with the zero trust, it's really saying this was the old world where we trusted the four walls of our data center and all of our security was at that front door. To now, as we come to a zero trust world, we're saying, I don't trust my network anymore. I want to harden the inside of it as well. And to do that, there's these four pillars. I need to know who are my human users. That's my human identity. I need to know who are my applications and machines. It's machine identity. And once I know those, I can govern them and say machine to machine, who's allowed to connect to who. human to machine, which users are allowed to connect to what systems. And that lets me move all of my internal systems to a zero trust model, right? And so there's different products in here to solve the different problems, but the foundation is starting with things like Vault and Terraform, so that you can manage all of this as infrastructure as code. You can have machine identity as the foundation of how we write policy, and then you can get more sophisticated with things like Consul and Boundary on top. And so all of that really comes back at the end of the day to this goal of we want to support our application teams and have one way, one set of doing things like security across all these different clouds in a very common approach, right? And all of this, you can kind of tell we're focused on the developers and how do we make it simple for them, right? So we can get out of their way, right? Because that's the business value. So I'll stop there. I'll be in the hallway, so feel free to come by and say hi and ask questions. And then we have 2 other great speakers talking to us after this. And thank you so much for joining. Thank you.